Hey there. In this video, we're going to talk about how to graph the inverse trig functions. We've already talked about how the inverse trig functions are defined. We talked about that in the last video. So make sure you're up to speed with that information before you go to this video. But assuming we're up to speed there, let's take a look at graphing the inverse trig functions. Okay, so what we have here is we have a graph of a normal trig function. In fact, this is the graph of y equals sine x. All right? We want to graph its inverse. Well, if you ask somebody to do that, what they should tell you is, well, that's impossible. This function has no inverse. Why is that? Well, what does the inverse do? The inverse takes a y value and produces the corresponding x value. Well, I could do that. I could take this y value, go over to the graph, go down and get the x. But that's not the only way I could do that. I could also take this y value, go over to the graph over here, and get this other value of x. Or I could take this y value, go over to the graph over here, and get this value of x. There's no one way to do that, and so there's no one way to define the inverse function. So this graph is failing an important property that functions need to satisfy to have an inverse, and that is the horizontal line test. If I draw a horizontal line, in order to have an inverse, the horizontal line must cross the graph at most once. But we see that this horizontal line is crossing the graph multiple times. And in fact, this needs to be true for every horizontal line that I choose. And we see that for lots of these lines, they're crossing the graph several times. In fact, if you extend the graph, you'll see that this line is crossing it infinitely many times, right? So that's particularly bad for us, okay? So there's no way we're going to get the inverse of this function. But what we can do is adjust the function a little bit. If we take this function and instead of looking at the whole graph, just look at this part from minus pi over 2 to pi over 2, then what we have is we have a function that passes the horizontal line test. Notice that any horizontal line will intersect this graph at most once. And so when we talk about finding the inverse of that trig function, what we're really doing is finding the inverse of this function. It's a slightly different function. It's a function that's defined only from negative pi over 2 to pi over 2. Okay, so how do we find the inverse? Well, the inverse, the graph of the inverse is obtained by reflecting the graph of this function across the line y equals x. That's that line there. So let's zoom in a little bit and see this happen up close. I'm going to reflect this line across that diagonal as if that diagonal y equals x were a mirror. What would I get if I did that? Well, this is the picture. And that is the graph of the inverse trig function. Now, what has happened here is that my original function, let's put it back up here, you'll notice that its height was at most 1 and it went down to negative 1, and it extended from negative pi over 2 to pi over 2. Well, the opposite is true for this function. This function is extending, its width is at most, it goes from negative 1 to 1, and its height goes from negative pi over 2 to pi over 2. We can adjust this by adjusting the labeling of our axes. There we go. Now you can see it. If I label the axes accordingly, we can see that that's exactly what's going on. In fact, this graph here is just a piece of this picture here. Now, what I'm showing you here is what would happen if we took the entire sine function and tilted it and reflected it across the line y equals x. Now, this is not the graph of a function, right? Because a function has to pass the vertical line test, and this is not doing that. But fortunately, that's not what we ended up with. We ended up with this. And this is, indeed, passing the vertical line test. This is a function, and this is a graph of the inverse sine function, or arc sine. What we're looking at is y equals arc sine of x. And a couple things that you should note about it is that its domain goes from negative 1 to 1, and its range goes from negative pi over 2 to pi over 2. And these numbers should be familiar to you from the previous video. These were very important to us when we were using our inverse trig function. And now we see where they come from. All right, now let's talk about cosine x. This is a graph of y equals cosine x. So first thing, if I want to find the inverse function, I need to chop this function off so that it passes the horizontal line test. Where would I chop it? Well, I can't contain this stuff because that stuff is violating the horizontal line test. Lines will intersect this bump more than once. So I have to start from the middle of the bump and go to the right until I get to about here. And that'll do it. There we go. What we're seeing here is the truncated graph over here, and this does pass the horizontal line test. So I can take this line y equals x, and I can reflect this graph across that line, and this is what I get. And we see that this is the graph of arc cos x, or the inverse cosine. Let me adjust my labeling of my axes, because we've got to put the pi over 2 labeling here and the 1 unit labeling here. There we go. And now we can see that it goes from -1 to 1. Its domain is -1 to 1, and its range is 0 to pi. And just like for sine, this range, 0 to pi, should be familiar to you from the last video. This was very important to us. When we compute arc cosine, we're always getting an angle between 0 and pi. Finally, let's look at the tangent function. We're here looking at y equals tangent x, and we see this is not an invertible function. It does not pass the horizontal line test. So what do? We truncate the graph. There we go. If I just take this piece of the graph, now it does pass the horizontal line test. So what I'll do is I will reflect it across the line y equals x, and there we go. This is the graph of arctan, y equals arctan x. And I'll make those adjustments. I'll relabel my x-axis and y-axis. There we go. And we see the graph has domain equal to all real numbers, and range, well, let's see, we can't really tell by looking at this here, but you can see as if I zoom out, the range goes from -pi over 2 to pi over 2, which again, from the last video, we knew that was an important aspect of the arctan function. It only returns angles in this interval. So we've seen graphs of this arc sine, arc cosine, and arc tangent. So now we know how to deal with these graphs.